So now we can go ahead and code up our Radford-Rice equation, and I have it on the left over here. This doesn't like working in groups very much. All right, so here's our Radford-Rice equation. And our goal is to determine the vapor fraction. And the reason we want the vapor fraction is because it gives us the ability to solve for all the liquid fractions and our ratios. So the very first thing that we'll define are our temperatures and our pressures that we're going to be performing this flash calculation at. We'll do it at 393 Kelvin and 150,000 pascals. And we also need to define our K because we use it in our equation. And our K is going to be equal to, there's two ways we can do this. We'll leave it as the PVAP, the saturation vapor pressure, divided by the total pressure. Then our Z, which is our feed rate in our scenario. In this case, it's going to be 4 moles benzene well, 40% benzene and 60% toluene. And then our feed rate is going to be 10 moles per second. And let's double check everything looks all right here. I just forgot a P. There we go. All right, and now we can actually define our Radford-Rice equation. And we want to be inputting a vector because we're going to be using a root solver to solve for our vapor fraction and then using that to solve for everything else. And in this case, we'll leave a vector, and then we also want to leave our temperature. And actually, we don't even need to pass in the temperature because we already defined our K up there. And then we want to end up returning, it'll be some form of our equation over here. So we'll go ahead and type this out. We have Z, well, just to make my life a little easier, our K term is equal to K minus 1, just because we use that twice. So we want to return our Z times our K term divided by 1 plus our vapor fraction divided by our, or multiplied by our K term. And I think I have something wonky going on. Wait, no? Okay, our parentheses are good. And then from here, okay, so our vector, we're passing in a vector because we're actually going to be using a root solver. And we want our Z to be the first term, or sorry, our VF to be the first term of our vector that we pass in. And we're actually going to be solving for the root. And in this scenario, we want our initial guess to be, well, actually our initial guess comes second in the root function. But we'll go with 298. Or, sorry, it's not in temperature. We'll go with 0.5. And I just forgot a colon here. All right, there we go. So now we can go ahead and define our liquid and our total feed, and then we can use that to solve for our vapor fractions of the outflows. So actually, we're not going to do the root inside of this equation. We're going to do it on on the actual function that we defined, and we want to return this as an array. So we'll work with our root solver. And then from here, let's make sure that all works. All right, and then our vapor fraction is going to be the root of this because our vapor fraction is the input into our Radford race equation in this case. So VF is going to be equal to the root for our Radford race, and then we'll use an initial guess of 50-50. All right, so it looks like our return on our Radford race. Oh, I just forgot a sum. All right, there we go. And then we can also define our vapor. Our mole fraction in the vapor phase is going to be equal to our VF times our feed rate. And then our liquid phase is going to be equal to our F minus our vapor phase. And then Y is going to be equal to K times X. And that just leaves X to define. So now we can go ahead and solve for our X term as well. And in this case, X will simply be as we derived it in our notes. I don't have them pulled up, but or you know what, I'll pull it up real quick. Here's our function for X, and then we simply plugged it in to our equation for yi minus xi, and then we should be good to go. Invalid syntax on y equals k times x. So that's interesting. I will be right back after I figure out what's causing that problem. All right, so we can go ahead and just display these. And I had an issue earlier. I forgot a single decimal point in our mole fractions. And I guess I didn't fix it. Let's rerun that. And that should solve our error here. These numbers are K values for benzene and toluene. All right, so we'll display our vapor fraction, our liquid fraction, and then the mole fractions and the vapor and liquid phase for each of our components. All right, so here we have the vapor component, the liquid component, and then the mole fractions for each of the vapor and the liquid components. So here, what this value is saying is that our liquid phase is less than 0 given these parameters. So basically we're just saying we have all vapor.